Welcome to all of you. Now we discuss Unit 2 2021 Mathematical Modeling, paper DSE A2.2, semester 6, B.Sc Mathematics Honors, University of Calcutta. Question paper 2021, Unit 2. Question 3a. Write a short note on Monte Carlo simulation method to find the area of the bounded region x square plus y square less than equal to 25, x greater than equal to 0, y greater than equal to 0. See the question paper 2022 DSE A2.2 Mathematical Modeling Unit 2 question 3a, and there there is also circle x square plus y square equal to 1, and that is less than equal to 1. This is less than equal to 25. So change accordingly and replace this non-negative curve, this y equal to root over of 1 minus x square, by this y equal to root over 25 minus x square, and the total area under this circle, this center is origin 0 0, and the radius is 5 unit, and pi r square, that is 25 pi square units, and this part of the circle, 1/4 of the circle, this between the region 0 to 5 and y 0 to 5 is contained within the square of sides 5 units. The area under the shaded region is 25 by 4 pi square units. Be careful about the intervals. This in the question paper 2022 there is 0 less than equal to x less than equal to 1, and here you must use this 0 less than equal to x less than equal to 5 and 0 less than equal to y less than equal to 5, and fxi equal to root over of square root of 25 minus xi square. Next question, describe middle square method to generate random numbers starting with a 4-digit positive integer seed, say x0, and start one of its major drawback. Middle square method, step 1, start with a 4-digit number x0, and step 2, square it to obtain an 8-digit number at leading 0 if necessary, and take the middle 4 digits as the next random number. Consider this example. First, this seed takes seed x0 as 2041, 2041. The step, this n is step, initial step 2041, square this 4165684, 1, 2, 3, 4, 5, 6, 7. This square of these 7 digits. So add this leading 0, this one leading 0, so that total number of digits next square is 8, and delete 2 digits from the beginning and 2 digits from the end, and this middle 4 digits, take this middle 4 digit 1656 1656 as the next random number. Next step. So step 1, this is the 1646456 is the random number, and square it and add this leading 0, so that total number of digits in this square is 8, and take this middle 4 digits, this 7423, and so on, so on, so on. And this, we observe that at the 12th step, this random number is 0 0 0. So this major drawback of this method is that it has tendency to degenerate to D0, where it will stay forever. So if we square this 0 0 0 0, so again 0, again 0, and so on, so on, so on. Next question, a small harbor has unloading facility for ships. Only one ship can be unloaded at any one time. Ships arrive for unloading of cargo at the harbor, time span between the arrival of successive ships, and unloading time of the 5 ships are given in the table below. Find the average time spent by the ships in the harbor. This is the time between successive ships in minutes, and the second row unloading time in minutes, ship 1, ship 2, ship 3, ship 4, ship 5, and this first row the time between the successive ships, and the second row unloading time. Now we draw this uh, diagram for this loading, unloading time and waiting time. This is the initially this starting from 0 minutes. Uh, this time is in minutes. So after 5 minutes, sorry, 15 minutes, first ship enters in the harbor, and then from 15 to up to 65, so up to 80 minutes, this unloading time for ship 1 is 65 minutes. And after 15 minutes, this after 35 minutes, entered the ship 1. Second ship enters in the harbor after 35 minutes. So 35 minutes after this 15 plus 35, that is at the point 50 minutes. So the second ship enters in the harbor, and this up to 80 minutes, that is 80 minus 50, that is 30 minutes, and this is the waiting time for the ship 2. Um, from the 80 minute to 135 minute, this is the unloading time for ship 2, because this 80 plus 55 is the 135 is the unloading time for ship 2. And ship 3 enters the harbor after 20 minutes of ship 2 enters. So this 50 plus 20, that is at the point 70 minutes, this ship 3 enters in the harbor, and this 135 minus 70, that is 65 minutes, is the waiting time for ship 3. And this unloading time for ship 3 is 60 minutes. So 135 plus 60, that is 195 minutes. At the 195 minutes, this unloading time for ship 3. And the ship 4, this enters the harbor at the 170 minutes, and this is the after 100 minutes from ship 3. This waiting time is 25 minutes and unloading time is 70 minutes. And this is the ship 5, waiting time is 60 minutes, unloading time is 80 minutes, and this. And we construct this table, ship 1, ship 2, time between ships arrival, and this first ship 15 minutes, and this is the first column. Actually, this is the first row. This is the first row. This time between the ship's arrival. Arrival time. So arrival time 15, 50, 70, 170, 205. Actually, this 15 plus 35, 50. 50 plus 20 is 70. 70 plus 100 is 170. 170 plus 35 at 205. And start service, this for the first ship at 15 minutes, and second ship start service at 80 minutes, and for third ship start service at 135 minutes, and so this on this way. And this for ship 4, this service starts at 195 minutes, and ship 5 service starts at 265 minutes. And queue uh, length uh, queue length at arrival of the ships. So for the first ship, there is no queue. When ship 2 enters in the harbor, there is only one ship. So for ship 2, there is one queue. And when ship 3 enters in the harbor, there are at this point there are previous two ships, ships 1 and ship 2. So this queue length is 2. And other ships, ship 4 queue length is 1, ship 5 queue length is 1 also. Waiting time is the first ship no waiting time 0, and second ship 30 minutes, and for third ship 65 minutes, and for fourth ship is the 25 minutes, and this fifth ship is 60 minutes. And the unloading time is actually, this is the this column is equal to the second row of this given column, given box, given table. So this unloading time and time in the harbor, total time, actually first ship total time is 65, and for the second ship it will be 30 plus 55, this 85 minutes. So this 30 plus 55, and 65 plus 60 is 125, 25 plus 70 is 95, 60 plus 80 140 is the time of the ships in the harbor. So total waiting time is 180, divided by 5 is the average waiting time, and this is the unloading time. Total unloading time 330, and the average unloading time is 66 divided by 5. This time in the harbor of the ships is total 510, and the average time uh, spent on this harbor per each ship is 102 minutes. Hence, the required average time spent by the ships in the harbor is 102 minutes. Next question. A farm makes two products, P1 and P2, and has production capacity of 18 tons per day. Total production capacity 18 tons. P1 and P2 require same production capacity. So P1 production capacity 9 tons and P2 production capacity 9 tons. So this is the set this x1 and x2 and number of products per day in tons. P1 products x1 tons per day, and P2 products say x2 tons per day. And production capacity per day, and this the 9 tons per day, and this 9 tons per day for P1 and P2. The farm must supply at least 4 ton of P1 and 6 ton of P2 per day. So at least this is the least demand of this production per day in tons. This is the P1 products at least 4 tons per day, at least 6 ton per day for P2 products. Each ton P1 P2 requires 60 hours of machine work each. So machine time per tons machine in hour, this time in hour 60 hours per tons, 60 hours per ton per tons, and 60 hours per ton. And profit per ton for P1 is 160 and P2 240 per ton in rupees. And total production is 18 per day, production capacity 18 tons per day. And this machine time, actually total machine time is this given this over 720 hour. Total machine hours is 720 hours. And we construct this mathematical model of this LPP. This maximize Z, this profit 160 into x1, 240 into x2. This is the objective function to maximize this, and subject to the constraint this 60 hour per ton. So for x1 ton, this 60 into x1, and for x2 ton, this 60 into x2 is the total hours for production of x1 tons and x2 tons of the products P1 and P2 respectively. And this less than equal to 720 hour. And this is the available time, total available time 720. So less than equal to 720. And the least production for P1 is 4. So 4 less than equal to x1. And the production capacity, maximum production is for P1 is 9 tons per day. So x1 less than equal, 4 less than equal to x1 less than equal to time, and 6 less than equal to x2 less than equal to 9. And where x1 and x2 are greater than equal to 0. Use graph paper for drawing this graph. So this x1 axis, this x2 axis, and this first we convert this inequality as equation, and for this equation draw this graph, this line, and this is the x1 by 12 plus x2 by 12 equal to 1, and x1 equal to 4 is x1 equal to 4, and x1 equal to 9 is x1 equal to 9, and x2 equal to 6, x2 equal to 6, and x2 equal to 9. And this inequality, set all this inequality, and this is the cell region PQR. This is the required convex region for feasible region for solving these the vertices of this region is P, and solving this, and 4 6 and R Solving this line and this line, x equal to 6, we get 6 6, and q is the, solving this line and this line, we get q is the 4 8. Now we find the value of the objective function, this z, at this point p q r. Because we know that for finite convex region, the maximize or minimize objective function attains at the vertex point. So ZP at this point is equal to 2080 rupees, and ZQ is the ZQ at the point Q 4 and 8 is 256, and ZR is the 200 2400. So maximum is this ZQ at this point ZQ. So the optimal record optimal solution, that is maximum solution, is x1 equal to 4 tons and x2 equal to 8 tons, and maximize Z equal to 2560 rupees. This is the answer. Next question, given an average arrival of 20 per hour, is it better for a customer to get a service at a single channel with mean service rate of 22 customers, or at one of the two channels in parallel with the mean service rate 11 customers for each of the two channels? Assume that both queues are this model M by M by S, infinity, Fi Fo, first in first out, Markovian is this. And this is the same question as 2022 mathematical modeling DSE paper A2.2, question number 3H. Question 3A. Solve the problem algebraically to get an optimal solution. Maximize 25x1 plus 30x2 subject to 20x1 plus 30x2 less than equal to 690, 5x1 plus 4x2 less than equal to 120, x1 x2 greater than equal to 0. Now we write the standardized form of the given LPP as this: maximize z equal to 25x1 plus 30x2 plus 0s1 plus 0s2. This s1 and s2 are slack variables. This is less than equal to sign, so we put here first equation, convert this equation using this, adding this slack variable x1, and for the second equation, adding the slack variable s2, convert this inequality into equation. And x1, x2, s1, s2 are all greater than equal to 0. Here, the number of original variables, these x1 and x2, so n equal to 2, and number of constant, so there are 2 constants, so n equal to 2. So number of basic solutions that equal to m plus n cm. So there are 6 basic solutions. To get basic solutions, set any 2 n variables out of 4 variables, is x1, x2, s1, s2, m plus n variables equal to 0. And these variables are called the non-basic variables. And then solving for remaining 2 variables, we construct this table: serial number, basic variables, non-basic variables, that is equal to 0, put, and values of the basic variables in the reduced equation after putting this non-basic variable to 0, and this reduced equation, and solution of this, and the value of the objective function, and this feasible solution or not. Now set x1 and x2 basic variables. So remaining 2 variables s1 and s2, non-basic variables, put s1 equal to 0, s2 equal to 0, and this reduced equation is this, and solving this reduced equation we get x1 equal to 12 and x2 equal to 15. So the required solution is this: 12, x1 12, x2 15, s1 0, s2 0, and putting these values of x1 and x2 in the objective function 25x1 plus 30x2, we get the value of the objective function 750. And then next, a basic variable x1 s1, non-basic variable x2 s2, and this reduced equation, this solution, objective function 600, and this feasible solution, and this next basic x1 s2, so non-basic x2 s1, the value of this, actually this s2 is negative, so we did not calculate the value of the objective function because it is not feasible solution. And next, basic variable x2 s1, non-basic x1 s2, and this S1 is negative, so this is not feasible, and because S1 is negative. Next, basic variables x2, s2, non-basic x1, s1, and this value of this x2 is this 23, s2 is equal to 28, and the solution is 0, 23, 0, 28, and the value of the objective function 690. And last 6 basic variables set x1, s2, non-basic variables x1, x2, and this we get the solution this, and the objective function is 0, and this variable solution yes. So from this column, we see that the maximum value of the objective function is 750. So this is the maximized problem. So this is the maximum value of z. So correct optimal solution is this x1 equal to 12, x2 equal to 15. Next question. Following the optimal table of the LPP, maximize z is equal to this subject to this. This the final table is this. Question is that determine the range under which the components C2 of the profit vector can vary so that the current optimal solution remains optimal, and determine the range under which the component B2 of the requirement vector can vary to maintain the optimality of the current optimal solution. From the final table, we see that optimal solution is this y46, that is x actually this the x1 is 0, then no x1 is here, so x1 is 0, x2 equal to 4, this y2 equal to 4, so x2 equal to 4, and this x3 equal to 0, and no x3 here, so x3 equal to 0, and x4 equal to 6, and x5 equal to 10, and x6 equal to 0, x7 equal to 0. Here x1, x3, x6, x5 are non-basic variables because in this table these x4, x2 and x5 are basic variables in the final table. So x1, x3 and x6, x7 are non-basic variables in the optimal table. We want to find the permissible limits for C2, and C2 is the corresponding to the basic variables because x2 present here. x2 is the basic variables here. So C2 is the corresponding to the basic variables x2. So the above solution remains optimal. Let C2 dash, this new value of C2, equal to C2 plus delta C2. And delta C2 is the very small change in C2 so that the above solution remains optimal. Now y2j, because C2, so y2j is the 0, 1, 1, y2j is this 0, 1, 1, 0, 0, 1, 0. We consider those y2j for which j corresponds to the non-basis vectors, that is j is equal to 1, 3, 6, 7. Is 1, 3, 6 and 7. So 1, 3, 6, 7 is this, that is y21, y23, y26, y27, sorry, and this is 7, y27. So this 0, 1, 1, 1, 0, 1, 3, 6, 7, 1 is 1, 3, and this 0, 1, 6, 7, 0, 1, 1, 0, 0, 1, 1, 0, non-basic variables for these non-basis vectors. Now the formula is this: maximum over j not equal to 2, this minus zj minus cj whole divided by y2j when y2j greater than 0, less than equal to delta c2 less than equal to minimum j not equal to 2, minus zj minus cj by y2j where y2j is less than 0. So zj minus cj is this, zj minus cj 1, 0, 3, 0, 0, 2, m. So zj minus cj corresponding 1, 3, 6, 7. So 1 is 1, this 1, 3, this 3, 6 is 2, 7 is m. So put here, and this minus, so minus 1, minus 3, minus 2, minus m. Now this 0, 1, 1, 0. So put here 0, 1, 1, 0. But this y2j greater than 0. So this 0. So cancel this ratio. And so we get this, and minus 3, minus 2. Maximum of this is minus 2 is the maximum. So minus 2 less than equal to C2. and there is no y2j negative, so this is infinity, so less than infinity. So adding C2, C2 minus 2 less than equal to C2 plus delta C2 less than C2 plus infinity. So 2 minus 2 less than equal to C2 dash less than infinity. That is 0 less than equal to C2 dash less than infinity. So C2 dash, that is new value C2 dash, is greater than equal to 0. And this is the required range for C2 without affecting the optimal solution. And next question, part 2, determine the range under which the component B2 of the requirement vector can vary to maintain the optimality of the current optimal solution. Here, B inverse B is equal to XB. XB is the 6, 4, 10, because this table is 6, 4, 10. XB, B inverse B. And B is the vector, this 10, 6, 4. This is the vector 10, 6, 4. And the B inverse B11, B12, B13, and so on actually is Y4, Y7, Y6. Actually is Y4, Y7, 0, 1, 0, 0, 0, 0, minus 1, and Y6, minus 1, 1, 4. Actually, this is the columns, this is the initial basis matrix for this column 1, 0, 0, 0, 1, 0, 0, 0, 1. So we B inverse, let this B inverse this. Let B2 dash equal to B2 plus delta B2. This delta B2 is the small changes of B2, so that the optimality conditions remain satisfied. And so this x4, x2, x5, because this table x4, x2, x5 equal to B inverse B dash. So B inverse is this 1, 0, 0, 0, 0, 1, minus 1, 1, 4, and B dash is this 10, 6, 4, add 6 plus delta B2. B2 is the B2 plus delta B2 is greater than equal to 0. So multiplying these two matrix, we get this. Hence 10 minus delta B2 greater than equal to 0, or delta B2 less than equal to 10, add this. So minus infinity less than delta B2 less than equal to 10, adding B2 on each sides, so we get minus infinity less than B2 dash less than equal to 16. This is the required range for B2 dash. Next question 3H. A departmental store has only one cashier. During the rush hours, customers arrive at a rate of 20 customers per hour. The average number of customers that can be handled by the cashier is 24 hours. Assuming the conditions for use of the single channel queuing model, find out the following probability that the cashier is idle, and this average number of customers in the system, average time of customer in the system, average number of customers in the queue, and average time of customer spends in the queue. Here the model is of the type MM1 single channel, and this infinity FCFS, first come first serve. M for Markovian distribution of arrival of the customer, Markovian distribution of the departure of the customer, and this one is the single channel system. Infinity, capacity of the system is infinite. FCFS, first come first serve basis service. Now the arrival lambda is the 20 by 60 because this rate 20 customers per hour, so 60 minutes per minutes, this 20 by 60 customers per minute is the arrival rate, mean average arrival rate is, and mean service rate mu is equal to 24 by 60, and because this 24 per hour handled by customer 24 per hour, so this, and the utilization ratio rho is the lambda by mu, that is equal to 5 by 6. The probability that the cashier is idle, that is the probability of the having no customer in the steady state of the system, that is P0, that is equal to 1 minus rho, so this is 1 by 6. Average or respected number of customers in the system, that is LS, equal to rho by 1 minus rho equal to 5 by 6 by 1 minus 5 by 6, that is equal to 5. Average or expected time a customer spends in the system, that is in waiting time plus being served. So WS is equal to LS by lambda is equal to 5 by 1 by 3 equal to 15 minutes. And number 4, the average or expected number of customers in the queue, that is LQ, equal to ls minus rho, that is equal to 25 by 6, approximately equal to 4. And this average time customer spends in the queue, WQ, that is equal to LQ by lambda. So LQ is this 25 by 6, and lambda is the is this 1 by 3. So average time customer spend in queue, and this average time customer spend is system waiting and being served, and this the so this 15 minutes is the 12.5 minutes here average spend in the customer. Thank you for watching this video.